In today's session, I am going to explain about the DC machines. Here, this is the one of the important topic which is coming in many competitive examination view. And here, before going to discuss about the construction of a DC machine, we have to know in the entire power system how this DC machines as a DC generator or a DC motor is coming and what is its application. To understand that one, we have to analyze the entire power system by using a single line diagram. In the single line diagram, the first part is generation and later on its second part is distribution and finally load. Here in this entire three section, it is very easy for us to analyze the entire power system. That is, the first one is generation, and the second one is transmission, and the third one is the distribution. In this, the first part we are going to focus here, that is the generation. We are having the different sources to generate, like hydropower is there, hydro water as a source, and the nuclear, diesel, all these sources are available. To extract the power from these sources, we need a generator. A generator may be a size which is from 1 kilowatt to a megawatt, its variation is there. So according to that, we need what is its construction, how it is helpful. In this diagram, we see the application comes here to convert the mechanical energy into electrical energy. With the different sources, we need a generators. It means that there is varieties of generators are there, like long shunt, short shunt, and then according to its applications, we need a small and large type of generators, and we will see the construction. Along with that, I will explain the important questions which appear in the previous examination in the competitive exams. The second part is in the transmission, where it requires the step-up, step-down transformer and the various transmission like long transmission line, short transmission line, and then the medium transmission line. Finally, in this, the load distribution, we need some distribution of the inductive type of load, capacitive type of load, and resistive type of load. Here the major is the motors which are of either a DC motors or in the inductive type of motors. All these motors will come under this load. Now here our basic interest is towards the DC machine. The DC machine construction, you just observe it over here. This is the cross-sectional view of this, in which there is a lifting eye and a pole core, pole coil, pole shoe yoke, and the rotating part here, the shaft armature, where that is the rotating part. It means that this entire construction of the DC motor is classified into two types. That is, the first one is a stationary part, and the second one is rotating part. In the stationary part, this is the yoke, which is made of cast iron, or for the large DC machine, it is made of cast steel. It is for smaller size of machine, it is made of cast iron, and for large machines, it is made of cast steel. Then what is the advantage of make into a cast iron or cast steel is this cast iron saturation level is of 0.8 Weber per meter square, while in case of cast steel it is of around 0.8 Weber per meter square. So here the flux density is become a saturate in the cast iron for 0.8 Weber per meter square, while in case of cast steel it is of 1.5 Weber per meter square. Then what does it mean? How it is helpful? If for the larger machines, if we use a cast iron as the yoke, which is the outer periphery and cylindrical in shape, then what happens? The size of the machine goes on increase, then definitely its weight is increased, and whatever be the place required for the installation of this generator or in case of motor, that space also increases. Hence it is not economical. To make a best suitable one for the outer periphery of this machine and make it a smaller diameter for the same applications, then the preferable is cast steel material, which is of 1.5 Weber per meter square. The next part of this is the poles, which is fixed with the yoke by using the board system, and here the pole shoe, and there is a winding. This is the winding, which is of copper made. And what is the use of this? We need a flux density here. That flux is produced by using this entire system, that is a pole system. That pole system consists of three parts, that is of pole core, pole coil and pole shoe. This system of made of some cast iron materials, and here this is fixed by using the board system. Whenever there is a machines under the running conditions, that has to be hold in. And next part of this machine is this rotating part, where in the next part is the rotating part of the DC machine, in which the armature is the rotating part here. This armature outer periphery is cut with the number of slots. These are the slots, and conductors are placed in these slots. These are the conductors, number of conductors which are placed inside these slots. These conductors are laminated each other, as well as the periphery of this entire cutting slots is laminated. And here for the laminations we are using a high permeability materials, that is of cast steel, and low loss cast iron materials, which is cast silicon, which is used as the insulation. And the insulation level in this case is of around 0.4 to 0.5 mm of thickness. And the next is the commutator. In the commutator, which is the essential part in this construction of the DC generator, because whatever be the power supply, because of this dynamically induced EMF, when it is cut by the armature conductor is produced, it is in the form of sinusoidal in nature. It is in the form of sinusoidal in nature, but we need here to connect for outer periphery, that is load, in the form of DC. So here, to convert this AC into DC, we need this commutator. And in the many examinations, of GATE or any other competitive exam, this is the repetitive question in which they ask the in the DC machine, commutator function is, the options will be like this. It converts DC into AC or AC into AC or AC into DC and then DC into DC. The option here is it's used to convert AC to DC. That's the one of the important question in this construction of the DC machine. And finally, the shaft in which we connected the brushes. That brushes is made of carbon or carbon graphite, and that is fixed with this commutator by using a spring which is connected continuously with the rotation, and we are extracting the power from this. That's the construction of this entire DC machine. Now we will move for the EMF equation of this DC machines, in which we are having Z as a number of conductors, and phi is the flux density, N is the speed in terms of RPM, that is nothing but a revolution per minute, and P is the number of poles, and A is nothing but the number of parallel paths. Now here in this number of parallel paths means what? Here for the winding which is in terms of progressive or retrogressive in nature, that is the coils are framed in the form of winding, that winding are either in the progressive or retrogressive one. Here if it is in the clockwise direction, then we are calling it as in the progressive. If it is in the anti-clockwise direction, then we are calling it as retrogressive in nature. Now here the number of parallel paths, according to this there are two types of windings, that is lap winding. Another one is wave winding. Here this is the progression of the winding in terms of lap, that's why we are calling it as in the lap winding, and where this progression of the winding in terms of it comes in under terms of wave shape, that's why we are calling it as a wave winding. So here the number of parallel paths in the lap winding is equivalent to number of poles. A is equivalent to number of poles, and where in case of wave winding it is always equivalent to 2. Number of parallel paths are always equivalent to 2. Therefore, to derive this EMF equation, which is very important one for the answering of the objective questions, because in many times it is appeared to calculate the speed or calculate the number of poles or parallel paths or EMF induced. So on that view, we have to understand about this EMF equation of the DC motor. So here to calculate that EMF equation, we know that here the flux cut by a conductor in one revolution equals phi p, that is nothing but flux in poles, that is change in flux. According to this Faraday's laws of electromagnetic induction, what happens when the flux is linking to the electrical circuit and it is changes, then what happens? A EMF will produce. EMF is produced. This produced EMF is of dynamically in nature. That change in flux we are considering here, that is phi into p, and then the revolution means this armature is due to the influence of the south pole and the north pole, it gets rotated, and its rotation is considered as per minute, that is nothing but 60 divided by n. per second, that is change in time. Hence EMF induced in one conductor is equivalent to d phi by dt, that is nothing but 5p, and substitution of this dt is 60 by n, therefore 5p n divided by 60 volts per minute we are getting here. And we know that EMF induced per parallel paths is equals EMF induced per conductor into number of conductors per parallel path. When we will substitute here, when we are substituting here these both d phi by dt, then we are getting this 5p 60 by n. When it goes towards the numerator, then it is 5p n divided by 60, and the multiplication with the number of conductors and the parallel path, we are finally getting the equation E equals 5z np divided by 60 into A. This is the EMF equation. And for the examination point of view, either in the objective type, competitive exam, or in the final exams, the problems are appear on this for the calculation of EMF induced, or a speed, or a number of conductors. So for that, here one example I have taken. In this example, a 4-pole, that is 1500 RPM DC generator has a lap pole armature having 32 slots and 8 conductors per slot. If the flux per pole is 0.04 Weber, calculate the EMF induced in the armature. What would be the EMF induced if the winding is wave connected? If the winding is wave connected. So here, to solve this problem, we have to understand what question is asked and what are the given data. So here, when we will see a 4-pole means the given data here p equals 4, and speed is n, that is of 1500 rpm, and then DC generator has a lap pole armature having 32 slots and 8 conductor per slot. It means here in this entire armature there are total number of slots are 32, and in each slot there is 8 conductors. Therefore total number of conductors Z equals number of slots into number of conductor in each slot. Number of conductor in each slot. Then what is the given data? That is 0.04, that is nothing but flux is given, that is 0.04 Weber, and it is asked calculate the EMF induced in the armature. So question is we have to calculate armature EMF which is induced in the armature, and what would be the EMF induced if the winding is wave connected. So what is the difference that we have to observe here is, it is asked the EMF induced in the armature and when it is wave connected. Then how to solve this problem? First we will solve the first one by knowing this EMF equation. E is equals to 5z np divided by 60 into A, and by substituting all this data we are getting here phi is of 0.04 and Z is 32 into 8, and flux, then speed is 1500 rpm, and P is 4 and 60 into. Now in case I told here for lap winding A equals to P, in the given problem A is equivalent to 4. Therefore here for the lap wound EMF induced, lap wound A is equals to P, that is nothing but 4. Therefore here it is 4, and when we will calculate it is of around 252 volts. Then Second part, what it is asked here is EMF induced in the armature. What would be the EMF induced if the winding is wave connected? Now here, for wave connection, we know that A is always equals to 2. Now substitute here in A, number of parallel paths is equals to 2 for wave winding. Then we are getting the answer, that is 32 into 8 into 15 into 4 divided by 60 into 2. When we will calculate this, it is of around 512 volts. So from this, what we conclude here is, for large machines and for high voltage and high current applications, we need wave winding shape or wave winding type of machines, and for small voltage and small currents, we need a lap wound type of DC machines. And in the competitive exam, it is asked about, by giving this question, they will ask what is the induced voltage when it is a wave connected, and they will give the options in all the concept, that is 252, 512 and 300, 360, like this. You have to understand, if you understand this concept of solving of the problem, then it is very easy for you to opt this option. Thank you for today's session, and in tomorrow's session I will continue with some induction motors.